let me introduce Jochen Cremer. Jochen Cremer is an associate professor at Technical University of Delft. He's also the co-director of the AI Energy Lab there, and the principal scientist at the Austrian Institute of Technology. He has done a number of things. He's mostly focusing on statistical machine learning and power systems, and we're looking forward to your talk, Jochen.
Great.
Very happy to have you here.
Thanks. So I hope the mic is also working. Perfect. Yeah, thanks first of all for the invitation. It's my first time here at DTU, so really appreciate the invitation to the organizing team. Thanks. Yeah, so today I'm talking about machine learning application within the area of power system reliability. But before I would like to mention a few things, introducing my team and my background. So I studied in RWTH Aachen University, where I was exposed to electric engineering and other engineering disciplines. And then I learned a few things about the computational methods, operations research, control. And I focused then in my PhD on machine learning for specifically dynamic security assessment as one of the applications I'm also introducing you today to. And as you can see, these loops are becoming smaller and smaller. So now I cross the ocean not that much anymore, but now I'm at TU Delft in the Netherlands. And the team I'm leading is based in Delft, Delft AI Energy Lab. So we focus on this application of machine learning to a number of topics, mainly focusing on monitoring and controlling of power systems. So we work with electrical system operators in the Netherlands, mainly Alliander and Stedin and Tenet together. And we have also then key education in our master program on application of machine learning to electric engineering and teaching electric engineers these basics. Maybe before I introduce the outline is who has done an introduction to machine learning course? Can you maybe raise your hand? Okay, so that's a lot. So I skip a few slides. I will be faster today. That's great. Okay, and who is actively using machine learning in their research? So it's also, let's say, 50%. That's great. Okay. So what I'm going to talk about today, so I split this talk in two halves. So first, I talk about reliability management and data and control rooms. So I will introduce reliability management for the ones of you who are not familiar with this. And then I will review machine learning approaches or concepts over the last 30 years or so. Then I dive into one of the applications where we applied security assessment. So this is dynamic security assessment with cost-sensitive supervised learning. So I go from supervised learning then in the second half of this talk to more advanced learning techniques, meaning learning with domain knowledge, state estimation with graph neural networks, and then I present to you weakly supervised learning and the application to also security, secure operations, so security constraint optimal power flow problem. And then I will outline the challenges which are still there when we apply into domain reliability management. Okay, so if you have any questions, now that I know you are familiar with Introduction to Machine Learning, we have more time, so feel free to raise your hand and ask time. Okay, let's start. So Introduction to Reliability Management. So where does this story start? So as you know, we are operating the system in these control rooms. And there are experts who are operating with tools, but primarily manually, the electrical system. And of course, they have gathered a lot of experience, which means they know how to use these tools very well, right, and to operate the system. Now, I borrowed this slide from Hitachi Energy, who has mapped out really nicely how complex this process is of deciding on the system operation within a system operator. So you can see that already decades ahead of time, you have things like infrastructure expansion planning. So where do you need the next transmission line? How do you interconnect countries? And then we have things like maintenance scheduling, outage management, which are done a year ahead, right? To plan 1 year ahead. At what time, what generator, what line may be in outage in the next year or years. And then we have the day ahead scheduling, we have intraday trading, So all of those things, as you can see, move forward in time towards the real time, right? That's the now. And then now you have, the system operator can still do a few things like grid switching, right? Just a little bit before operation, for example, or redispatching generators. And what is quite important is to be aware of the situation, right? So what is my photovoltaic intake? What generation can I expect? What is the demand forecasts and other things are really important, but also what are the security? What's the security of the operation? So we have N-1 criteria, for example. We would like to avoid power blackouts like we had in Spain a few weeks ago. And that's why it's so important to have these functions all interconnecting in real time and even being reactive. So if something goes wrong, you can have certain control functions, protection systems we have in place, voltage control, frequency control, and you name it. So it's all interlinking within each other, these different functions, and that's also where this complexity comes from. Because ultimately, if you think about this, interconnections is challenging manual rules which are brought in place by by the experts, right? Because this is not something which a single person is in charge of, but it's multiple teams. Actually, one team may be responsible for maintenance scheduling and a system operator, right? So you can see that all of these different functions are run by different teams, and they need to talk to each other. That makes the system very slow, specifically also when we innovate. So humans are here one of the bottlenecks, and especially in these time frames here, right? It's quite important to think about how can we automate, right? How can we automate these functions and the exchange of those functions or the interactions. And that's also what I'm focusing on in this talk and in this research, is really on problems or challenges which we have in these time frames, from minutes to milliseconds, because there is specifically that times where human cannot, because it's just too fast. We cannot decide so quickly, especially if multiple humans are involved. And how could this look like? So just to give you a teaser at the beginning of this talk of one of the applications is to predict stability with a method which is called neural ordinary differential equations, which was developed by one of the PhDs in my team, Mert. And you can see here a plot which could possibly look like this in a system operator, in a control room. And you see that we have here three phase angles, which at some moment are diverting. So you see that these are dropping, and at that moment, the system operator has one question in mind. Is the system secure, or is it not secure? And you can see the dashed curve, right? And that dashed curve was shortly after this fault, after this incident had happened, already available. So it's a prediction in the future of these dynamic states of the system. So it's essentially predicting the phase angle from after the fault has occurred. And what's interesting in this work is that it is taking the very beginning of the post-fault trajectory as input, so basically now, to predict the post-fault trajectory. And yes, it's not accurate. We know that we have these errors here in between, but what is interesting is that the curve here is converging to this steady state. Right? So we can still get something out of it. And why do we do all of it? Obviously, it's to avoid these worst cases, right? Even if you have just a few seconds afterwards and you have already information about what are the dynamics going to look like in the future, you can possibly avoid these worst case scenarios, such as the power blackout back in 2021 in Texas, or this power blackout in Spain and Portugal. And don't ask me about these causes, because I don't know, and I think there are little people who know yet. But what is interesting is that you see that there were a number of generation losses in time which led to this power blackout ultimately. So you had a number of generation losses in a sequence of time. And if you want to know more, you can also contact a friend of mine, Louis, who has analyzed this over the last few weeks, updating always new information as they become available. And so you see that already at 12:20, so that was 12 minutes before this blackout, there were some oscillations. Then you have here an n-1 fall, the first one, which was 19 seconds before the second one. And you had a very fast evolving process of these cascading effects. And that's also the point I want to make. So firstly, we may need to consider not only n-1, but maybe n-2 or 3 falls in the future. And secondly, is that you can see here how fast this happens. It's just a second or a few seconds. Right? So we need to automate methods. We need to automate these processes. And that's where machine learning comes in. But let's first define power system reliability. So I took one of these definitions. There are multiple different ones. So power system reliability is the probability that an electrical power system can perform a required function under given conditions for a given time. Right? So what does this mean? So we have here these 5 different states of the power system where we could operate, and now we really think about this blackout. We have the normal operating condition. If now things divert from the normal operating condition, we move to alert state, and we may move to an extremis or emergency state. And this is already where we would like not to be, right, in those states. And if things go wrong, it can take certain hours or days to restore the power system, as that was also the case in Spain. So we would like to stay here in this normal operating domain, right? So that's the goal. That's also where we focus in reliability. So one of these functions which we need in this reliability management is called the dynamic security assessment. So what's the goal of conventional offline dynamic security assessment? So the goal is that we have the state of the system, and we would like to know if a fault happens in the system, if this happens, will the system be secure or not, right? We have different phenomena in this power system which could happen, but ultimately we are interested in this binary information. And how we could solve it is through numerical integration, through applying numerical methods. So solving, for example, the ODE system, the swing equations, modeling possibly even EMT simulations with converter control systems and a very advanced performing a very advanced simulation. The problem is that for larger systems, this is slow. So we take computational time to do so, and it is too slow to have this simulation accessible in real time. Right? And that's what we would like to do, to have in real-time dynamic security assessment. So there the objective is to know this exactly in this moment in time. Right? If this fault happens, then how are the dynamics looking like? Are we secure or not? Now, it's a bit challenging to do that not only for now, but also for future states. Because we have forecasts, and you all know these forecasts can be inaccurate. So it's not only one point we need to assess, but multiple points along this trajectory. And actually then you have uncertainty on those trajectories. And these can be loading conditions, for example, right, in the system. And we can create those conditions. We can simulate them, but it's just a large amount of data and simulations you need to run. For this information, is this point in the future secure or not, in the next day, for example, or the next hour? And you can imagine that for larger systems, this is really high-dimensional space, right? So you have a lot of different loads in the system. So each city could be one load, and then you need to sample those in a very high-dimensional space, all possible combinations. And that's also where we get to a boundary or limitation when we think about machine learning applications, because of what is called the curse of dimensionality. So I will explain this for a second. So if you think about, now forget about necessarily this dynamic security assessment, but think about a one-dimensional space where you collect some data. They have 3 different classes here, right? And you just separate this in 3 different regions. So you can see that here are 2 stars and 1 triangle in the left region. If you now have the same number of points, I think this is 11, in two-dimensional space, you can see already that some of these regions, here we have these squares, are not covered anymore. So you don't know what class is in these regions, right? And this illustrates now the challenge, because you need exponentially more data to cover that space in larger dimensions. As you move to 3 dimensions, you can see already there are significantly more cubes which have no points. So you don't know if you are secure or insecure, right, in these regions. That's the connection to the dynamic security assessment problem. So yeah. So as dimensionally grows, we have fewer samples per region. So back to security of power systems. So we are ultimately interested in not specifically the trajectory. I mean, there are also use cases to know the trajectory. But in this research I'm presenting, we are primarily interested in these labels, right? In the binary label, y equals to 0 or y equals to 1. So accordingly, this is secure or insecure. And later on in the talk, I have to say that I swapped those 2 labels to secure and insecure. But I will let you know when this swapping happens. Sorry for that. Okay, now the objective of using machine learning here is think about this high-dimensional space. You can create time-domain simulations, and then we can learn a security boundary. So instead of using the simulation in real time, what if we have trained a security boundary with machine learning? And then we're using this boundary to assess in real time the security of our operating condition, right? For that, we need to train this function f. So x could be here the loading condition, y is this 0 and 1, right? Y hat is because we have inaccuracies. So it's not exactly the label always, or the correct label always. So now the big question is, how can you train and use f, specifically in this high-dimensional space? And that's not a new problem. So it has been actually investigated since the 90s for this application of dynamic security assessment. On the one hand side, it shows you, as there were so many researchers which were following, that it's probably a promising idea to do so, because there is a need in a system operator. But also, secondly, is since 30 years we are working on this. And if you are, and it's maybe a bit too slow, but we have also now new techniques which we can investigate for this problem. And if anyone here is more interested in a review on what has been investigated in the last decades, I would really recommend this literature review by the group of Louis V. Henke, who is also has started this type of research 30 years ago or so. Okay, so now there is this idea to use machine learning, but why now? Why should we use now machine learning for reliability management? And it maybe is worth to reflect a bit on these challenges which we have in reliability management and on the opportunities. So on the one hand side, for the challenges, we know that we will have more extreme weather events in the future, right? So we may need to take more simulations in the future to assess the security of the system for these extreme weather events. We have also higher grid load in the system, so we get the system at with less safety margin, essentially, as we operate at a higher grid load. We have higher uncertainty through the implementation of renewable energies, so possibly even more simulation studies that someone needs to take. And thirdly, and the last point, fourthly, is we have a highly complex system, power system, right? So why now? So now we have a few new techniques in AI, and that's also what I present you today. We have at system operators, we have more models, we have better weather forecasting models, we have more data that we had in the past. So we can build upon this, right, with our research. And still, once we had trained, and that's really the key benefit here, once we have trained a machine learning model, it is very quick in predicting the security of the system. Okay, so that was already the first part, introduction to reliability management. Ask me any questions if you would like to. Yep.
Thank you. How important is monitoring for these kinds of reliability measurements? Because the way I understand it is that often these blackouts come in phases that are very short term, as you just shown, but also a very long term period before where you already have minor errors that are not really detected even, and then actually lead to those cascading effects throughout the system. So how important is an increase in monitoring for these models to really work?
Yep, great question. So monitoring, I also mean the assessment of the security. So whatever we know in real time about, for example, oscillations or so, the system operators can act upon. So meaning to place corrective control actions and changing the grid topology, for example, in real time, or generated redispatch, activating those. So that's all. So the earlier you know, even if it's just a few seconds, you may take those corrective measures. So that's why monitoring and situational awareness is so important. Okay. Yep, thank you. Other questions about reliability management? Yes?
How do you handle situations where there are multiple control operators on the same grid? So for example, in the Western Interconnection in the US, which is a very big area, there are 38 control areas, what used to be called control areas. They're called balancing authorities. So how do you actually deal with communicating between them and then actually activating actions when there are so many authorities? The way they deal with it now, basically, and Dick can correct me, is they overbuild the system. It's not really n-1. If you look carefully at the way they do the analysis, there are rules. You can only put so much power east of the Colorado River and so on. So have you, and there are multiple control areas in Europe, obviously. So how do you deal with that?
Yeah. I don't know actually. So, yeah, I mean, there are other, let's say, communication foundations which we take as granted, for example, fast data exchange, exchange of information in real time. Yeah, but it's beyond the scope of my research, at least. We perform studies for a system operator, Tenet, who is then in charge of their grid. But I haven't looked into on their grid, exactly. But then connection to other control areas. Yep.
But there is regional coordination centers that do the N-1. There is some coordination about the N-1 at least, but not for the dynamics so much. Yeah. There are some.
Thanks.
How can you, even after the fact, come up with this binary value if it's secure or not? How do you know in the end? And why would you choose a binary value? Because I guess having the blackout is the extreme, then you know it wasn't secure. Yep. But you probably want more examples where it's not secure, and then how do you draw that boundary?
Yeah. I mean, there are so many applications of learning, for example, regression problems, and not only this binary information, like actually this work which I presented here, this one, is not giving you the binary information. It also gives you the prediction of the trajectory. So it depends. In the past, people used binary because it's easy to interpret. You can interpret it very fast, and you have also the output dimensions at least kept very small. So then just a very small dimension. So learning in high-dimensional space, input and output is difficult. But if you can at least have the output in a smaller dimension, that's the idea why people looked into this as well. But yeah, that's probably not wrong. One answer to this. Yes.
Thank you for presentation so far. First, for using the idea of machine learning and data for improving security and avoiding blackouts, we know that these blackouts happen very rarely, and there are some rare initiating events that we don't know much about them. And we need data for using machine learning.
Yeah.
So how we can find this data for learning and for training or model?
Also a very good point. So I think I would point there to this review article. So there are lots of work who focused on sampling, creating synthetic data. There were works in the group here at DTU, in the group of Spiros, a few other groups who looked into this data generation part. Here's a very good overview about it. What I will focus on in this talk today is about, let me see. Yeah, it's actually just here, not the next point, but afterwards. How can we learn when we have so little data about insecure conditions, with an approach which is called cost-sensitive learning? So I go back to this question a little bit later. On the data generation part, at least for today, it's a bit out of my presentation. But maybe on a high level, you can learn a probabilistic model on historical observation, sampling from that model, for example. Okay, great. Yeah, thanks. Then I will move to the second point. So machine learning concepts and approaches. So we started in this domain, as I mentioned, many years ago, 1991. To apply supervised learning for surrogate models. And throughout the slides, I use, you will see a few times here some people who worked on this in my team in the last few years. So Federica and Ola Jevola are working on this, or have worked on this. So what is the idea of supervised learning? So you essentially learn a surrogate model. So we want to replace or have a surrogate of this dynamic model. We assume we know some model M of the power system. So we have the power system S, we have a model of the power system M, and then we have parameters X. So parameters X could be a loading condition. Right? And then the objective is to assess M of X, so to run a simulation, to assess the model, and very fast and often. Right? So that's the objective ultimately. Real-time dynamic security assessment, to do that very fast. So the surrogate approach is to generate a training database of previous simulations. So the combination of X and Y, right? And where you have obtained a correct label from the simulator, YI. And then we train a surrogate model. So this could be a neural network. It can also be any other model, F. With a supervised loss. So this could be the squared error. It can also be a different loss function, right? But which basically penalizes differences between Y and Y hat. That's in a way the signal for the function F to become accurate throughout training, right? And then we can use this function F for new operating conditions, right, which are beyond the training data set. And then the advantage is that we get a very fast evaluation of this operating condition X. That's the benefit. And then one of these applications is what I presented to you, real-time dynamic security assessment. There were many others who have done this. A very classic model is the decision tree, because it is interpretable to use decision trees. But we have moved on since then towards neural networks and others. What are the challenges with supervised learning is, firstly, what if the power system changes? So topological changes, for example, change drastically the dynamic response of the system, so you would need to retrain your model. Or also if M changes, so the model and the system could change, right? So ideally we would have this the same, that the power system and the model are very similar, but that's not always the case. So very often we have actually inaccuracy in our models. So that's also challenging as we are simulating with M, right? And we have already one inaccuracy between S and M. Now we get a surrogate model of M, so we are possibly even worse. And then we need a very large and representative training set because of the question earlier, right? We have very little power blackouts, we have very little insecure conditions, we need to generate them, right? And then we have this issue of curse of dimensionality, so you need to create a lot of conditions. So that's challenging. Now, of course, since a few years, there were other approaches to this, and one is the physics-informed learning. So what's the idea there? So the idea is, still you are interested to learn a surrogate model, but you are using the physical knowledge of the system, or of the model M, right? So what you have is you incorporate the physical residual in the system to penalize deviations of the physics. So you add an additional loss term here, which penalizes the difference between F and M, right? And that's interesting, right? Because there you can now use the physical model to advance the learning, right? To learn better models, so higher accurate models. What has been shown here also by the group of Spiros is that you get better generalization performance with fewer training data, right? And what you have is that, in essence, these two do not need to be the same. So you can create some conditions where you have labels, and then you take some other X where you don't have labels, but you can then use the physics to still learn with this data. However, there are also ongoing challenges which relate to the same as we had earlier, or very similar. So if the power system S and M change, you basically need to create new synthetic data to update your model, right? And that's challenging among other challenges. For example, that we have now multiple losses. It's not so easy to learn with multiple losses. So multiple loss terms, as it can cause instability in the training. And yeah, you have similar limitations like physical models. If the model of the system M is different to the power system, so if you have this model inaccuracy, you may learn a surrogate model for the model, but not for the power system. And now there is a third approach, which is called this weakly supervised learning approach, or others call it end-to-end learning approaches, where the idea is to build a loss function where when you do not have the exact labels. So essentially, if the simulator is unavailable or uncertain, or you have a simulator which is ill-defined or indirectly defined, so you don't use any labels in this learning approach. So you can see here the difference that we do not have Y anymore. We have just collections of X. And we tailor a loss function here on the model M, for example, and on this function F to provide the signal for the function F to learn. So there are a number of examples in the past which have investigated this approach. So for example here, task-based end-to-end learning for stochastic optimization, so to learn optimal power flow problems. So you have the function F, which is your wind forecast model, right? And then you take this wind forecast model and you take this in an optimal power flow problem, and you are now taking the cost function of the optimal power flow problem to learn the function F. Right? So it's not only learning the function F to be an accurate wind forecaster, but to give you wind forecasts which optimize the cost function of the OPF. So that's the difference here. So you take function F in the optimization problem M, right? And then you have a loss function which is your objective function of the OPF, for example, to learn ultimately the function F. So now, what are the challenges here? So we have, firstly, we have inexact supervision. We still rely on the function on M to be accurate, but we may have system shifts. So still the same challenge as beforehand. If the system or the model changes, you have you need to retrain, and very often we have very little data. And then the fourth approach is what is called the self-supervised learning. So self-supervised learning learns from context. So very prominently, natural language processes. So you generate, again, the input X only, and you define a self-supervised pretext loss. Right? For example, here you see this on language. Tell me your electricity. And then you can see a model which was trained on a lot of those contexts of text can now distinguish which word is now more probable. Is it consumption or is it mayonnaise? Right? So we will all agree that consumption is more likely, and that's also what the machine learning model can learn on this pretext. And then after you have learned on a lot of context, you can change the loss to something else. For example, to train now this large language model to be performed very well on a chat functioning. Right? That's, I guess we all know that this works with certain limitations, but it works quite nice to process text and answer us some questions we pose to the chat. So there were also applications beyond natural language processing. For example, weather foundational models. You have Earth system foundational models and other type of foundational models, and also more recently investigations for grid foundational models or load forecasting of users. Now the challenge is that's really ongoing research, right? So to define this context, to define this loss in electrical power system, right? For our use cases here in reliability. So that's, of course, what some people work on at the moment. Yeah. So now, the last overview, which I present to you on machine learning concepts, is graph-based learning, so graph neural networks. So graph neural networks are quite powerful for electrical system. They have also their limitations, but they are a promising method as they incorporate also the topology of the electrical system through the graph, right? So this means you may address this curse of dimensionality because you are learning local patterns. And in the second half of the talk, I will go into this a bit more. So this is just the overview of this. But how does it work? So we construct a graph with vertices and edges, where you have features on this node and edges. And then you apply supervised loss. So this can also be combined with physics-informed learning or weakly supervised learning. So it's more in model architecture, I would say, rather than a concept or approach. So it is really defining how this function f looks like and creating local patterns. So here, for example, for images, we all know that we can learn with convolutions very well, and for graphs, we essentially can do that with graph neural networks. So now there were applications in the electrical systems already, quite a few, over the last 5 to 10 years, or 5 to 7 years. So one is the graph neural solver for AC optimal power flow. We worked on the distribution system state estimation challenge, and that's also the second half of the talk. So I will present this research to you. Now, what are the challenges? So similarly, if we have model inaccuracies, so S is not exactly the same as M, because now we are learning with the topology, right? So imagine the topology is inaccurate. You may learn an inaccurate graph neural network. We have also challenges with long range dependencies. So there are also approaches which can mitigate this. But generally, graph neural networks are good to learn from neighborhoods, and so on and so forth. Okay, so that was the second piece, machine learning concepts. So, yes.
Thank you. Maybe contextually, I see that you keep saying that one of the challenges is the topology variation, and this is always the issue that TSOs in real time try to solve issues with some topological change, which means this is what you should expect. Is it not possible to, or have you also tried training an AI that can understand changes in topology as well, so that it could be more, I don't know. That's the question. Did you, in one of these methods, explore making AI understand the changes in topology in order to be informed on the decision they provide to to TSOs in either of the time frames?
Yeah, thanks a lot. Yes, so indeed there were many research which have looked into that. So the most straightforward approach would be to sample possible topological reconfigurations of the system. So thinking about the substation, so someone could reconfigure the substation, and then sampling from in that substation all reconfigurations, and then you have multiple substations, so you need to sample a lot of those conditions. So people have looked into that, but it's just adding to this curse of dimensionality. Because now then you have not only loading conditions, but you have also the possible discrete variations. And especially for discrete variations, so one of the research which we are presenting in IREP in 2 months is looking into this. So it's this paper here, Exploring Extrapolation of Machine Learning Models for Power System Time Domain Simulations. So there we demonstrate that specifically for these discrete changes, it's difficult to learn machine learning models. But it is for sure promising to look into these configurations, and many have studied it.
One of the ways that potentially is, like, since AI can understand pictures,
Yep.
and like taking snapshot of this grid, and then you can feed them images.
Yep.
And basically these images, when they see a similar image, they can now make a decision quickly.
Yep.
I mean, I don't know if this is something you are also considering.
Yep, absolutely.
Yeah.
So what I will present in number 4 here, and also number 5, is the generalization of convolutional neural networks to graph neural networks. So with convolutions, we can process these images very well. With graph neural networks, we can process graph or topological information very well. So the question is very nicely asked, and it's basically part of the second part.
I have a question on the input data that you use for training these models. So they are representations of the static version of the grid. What does it include? Is voltage, phase angles of every node in the network, and what is the granularity of this data? If you could share a few details.
Yeah. I mean, it depends a bit on the application. So for dynamic security assessment, we consider the full static state. So the phase angles and all information which are available. Power flows in the system, in AC, in one moment in time.
And these are extracted from real operations from Tenet,
Yeah.
in this case.
So we assume we have a state estimator, and then we take the output of the state estimator, steady state estimator, as the input to the dynamic security assessment.
Okay. And would it be possible to use software like Power Factory to generate not real operation data, but data that resembles operation, because you have a full model of the network there, and
Yeah.
use it to generate more samples to feel a bit the problem?
Exactly. So that's exactly the idea. So we do that, for instance, here. We generate a training data set where we generate this YA from the full simulator. So this can be your Power Factory or any other tool, but we always start from that. So we need to figure out how many of this do we need, but we take the model M as information to get the Y. So to compute different variations, different fault scenarios, and so on and so forth.
Okay. Thank you very much.
Wait.
Yeah. So.
Thanks for your impressive talk, and I have some questions related to the graph neural networks. So the first question is, I saw here you said that one of the benefits is generalization to the changes to topologies. So my question is, what's the changes to topologies? So for example, I can see maybe there are 2 kinds of changes. So for example, if you maybe you train the neural network on a relatively small graph, let's say maybe 118 nodes case, and then you test on a relatively larger graph, and another maybe because of like power outage, there are some minor changes to the graph topologies. So I just want to ask what's the details of the changes to the topologies. Thank you.
Yeah, great. Yeah, great question. So what actually when I say we, then I mean researchers, not only my team, have figured out is that variations in terms of on the topology, which are small, so n-1, n-3, n-2, so small reconfigurations of the system, works fairly okay with graph neural networks. But if you have something in mind, like you say, to go from one electrical system to another one, where you have maybe changes in terms of bus numbers of 70 to the order of 120 or to the order of maybe 1,000 even, that becomes challenging. Because then also the distribution of Rx, for example, changes a lot. So yeah, it's not straightforward to do that generalization to very different systems. And arguably, I mean, there are different ideas around. So there are use cases where it makes sense to train something like that. So one foundational model for all parts of for all systems, right? That's a very ambitious goal to do so. But it's also, I mean, if you can do that, that will be great, right, to do it. But from a system operator perspective, let's say Tenet or another system operator, their system does not change so much in terms of to these extremes you have in mind. It's not that we are going to build 30 or 50 new transmission lines in the next 10 years or the next few years. So there are smaller changes, and the grid stays fairly the same. It's more these substation reconfigurations, for example, which alter the topologies for n-1, or if there's a line in outage for a few weeks, these kind of things.
Yeah, thanks for your explanation. And another maybe related question is, so I see here in the approach part you mentioned it can be used in on some unsynced graphs, GPy. I just want to know the training process. Is that so? Maybe the graph structure is fixed, and then you input some different node features, or in the training process you change the graph structures so it can be tested on some unsynced graph structures. Thank you.
I mean, it depends it depends on the application. So I think these concepts I present are generic concepts, and it depends on the application. You may vary the way you train. Also, within graph neural networks, there are so many choices you can make. Right, so maybe later I can explain you a bit more when I come to the application of graph neural networks for state estimation, how we did it in that use case for distribution grid state estimation.
Okay. Yeah, my question is also a bit related, but rather like on the other side, on the challenge that you mentioned regarding the inaccuracies. So usually you don't always only have topology changes, but you also have the model mismatch. Did you do any work in quantifying the model mismatch, and if it has an impact on the performance, or whether the models are robust towards, for example, I don't know, that the line parameters are not correct, or something in the model is not accurate enough?
So my team hasn't. What we have been working on is distribution grid state estimation. So their topology, we have tap changer positions, for example, which are known to be very inaccurate in the database. So we know there is a huge difference in the low voltage states afterwards. So it has for sure a high impact if those are inaccurate estimated. On these transmission system level problems for dynamic security assessment, the very classic example is that a lot of inverters we don't know the controllers, so we need to make any guesses. And there have been many works on estimating these controllers or working with inaccurate control parameters and so on. But yeah, it's not what we have been focusing on in my group yet. But yeah. Okay. Yeah, thanks for the questions. I go to the next point, which is now security assessment with cost-sensitive supervised learning. So it relates to, so maybe at this moment I just share with you how I structured this talk for a second. So you can see that I walked you through this different concepts: supervised learning, then physics-informed learning, weakly supervised learning, graph neural networks, right? And you can see that in this next phase, or in this next part, I focus on them one by one. So I go for supervised learning here, then we go for the graph neural networks. I just change the order slightly, and then I present this weakly supervised learning, right? So some use cases within the energy domain. So let's go for this first part, supervised learning with cost-sensitive learning. So it relates back to the question about what if you have very little data on insecure conditions, so like power blackouts. So this is the slides I prepared, not knowing that most of you had introduction to machine learning. So I skip how neural networks work, right? Unless someone raises their hand and say, please explain. Okay. Okay, then I start here again. So I mentioned to you that system operators have these experts who are experts in these different functions, and they work together with the support of tools. So we may need some sort of explainable models or interpretable models to the system operator, so they can analyze the causes, for example. They can make use of these models not only for predicting security, but also to understand and work with these models. So that's rendered the need for interpretable models. And then decision trees be one of those models, and also applied. And I use this sometimes to illustrate, because often you can replace the model with a neural network, and the learning and so on would work in this very similar way. So also here, I just share with you how a decision tree makes decisions, right? So you have secure and insecure areas where you have sampled operating conditions. So this can be power blackouts or insecure condition. This can be normal operating conditions where you get back to a static security after a fault. And you have generated these labels with time domain simulations, what I showed you earlier. Right, and here I just showed this in 2 dimensions, x1 and x2. And then a decision tree, this was an actual decision tree which was trained on the French transmission system in the EU project iTesla in 2017, where you can see different locations where you have power, P, that's active power, and then you have Q, and so on, which were the features for this decision tree. Right? And then if you end up with an operating condition in this leaf node, you may classify this as secure. And if this is orange, then it's insecure, or something in between, because you have also red. Right? So that's also back to another question. What if you have not only binary, but multiple layer labels? Or what if you want to predict the full trajectory even? So decision trees have, on the one hand side, limited expressive power, because the decision rules are very, it's a combination of linear rules, but they have really good interpretability. So whatever we choose, if we now use decision trees or neural networks, what we need to think about is how can we evaluate this model, right? So now I'm focusing on this example of classification, binary classification. So you are interested in binary secure and insecure, right? So we have a predicted and an actual security limit. So this can be your security limit for the time domain response to a fault. And you can see that there is a mismatch between the predicted and the actual security limit. So there are some points, like this one, which are inaccurately predicted, right? So the color here is the predicted label. Now, you all probably know this matrix. Does anyone not know this matrix? Okay. Raise your hand if you know this matrix. Okay, great. Yeah, so you have predicted classes, you have true classes, so the confusion matrix gives you different true positives, false positives, and true negatives and false negatives labels. And this is, by the way, I have to say that now I'm swapping the notation of the label, right? So positive here means secure, and negative means insecure, which is, I defined this earlier differently, but just remember that. So now we have these 2 different type of accurate predictions where we want to actually detect power blackouts. So it's very good if we get these true positives And then we have two types of wrong predictions, where one of them is significantly worse than the other one. And that one we need to avoid, right? So if we think the system is secure, but it's actually insecure. So that's the false negatives here. Okay. Now we have these different metrics. We have the classification accuracy, where it's just the summation of the true positives and true negatives over all points. Then we have the precision, so true positives over the true positives and false positives. And then we have the recall. And here, it's the true positives over true positives and false negatives. Right? And that's the ratio of correctly found insecure cases to all insecure cases. And that's what matters to us when we are learning for insecure conditions. We are interested in the recall. Right? So now, what I can also mention to you is that one decision tree or a support vector machine, you can operate in different ways. So you can essentially choose how high, you can choose how much important is the precision versus the recall. Because if you have here this support vector classifier, you cannot get it perfect. You cannot, or it depends on the learning problem you have, but you cannot be here at this point 1, 1, right? So this is the characteristic curve of one trained support vector machine, where you are changing the decision threshold, essentially. So the classic, you get a score from support vector classifier, right? If the threshold is now, the score is above 0.5, you assign one binary label. If it's lower than 0.5, you assign the other binary label. And you can now move this threshold from 0.5 along this curve, and you get a different recall and precision. Okay, so that was just to refamiliarize yourself with this kind of machine learning concept from which you may be familiar with. Are there any questions about that? Okay. Yeah, so I mentioned that the recall is the important one because we want to get this number high, so a lot of true positives, right? Because it's over all insecure cases. So it puts it in relationship to the true cases, right? The precision would put it to the predicted insecure cases. So that's the difference between these two. And now it's a bit tricky because you really want to avoid power blackouts, right? You really want to avoid this at all costs. So this means there's a huge cost imbalance in assigning these predictions, right? So the false negative is significantly higher than the false positives. So what if you are thinking there is an insecurity, but it's actually not? What you put is, as a system operator, you just add some corrective control, you mitigate, you do something to prevent the worst case, but it's not that costly. Right? So it's maybe the cost of some redispatch or so, or maybe a topological switch in a substation to find a better, more secure reconfiguration of the system. So that's very cheap in comparison to the impact of these worst case scenarios. Right? So there is this huge cost skewness between the false negatives and false positive. So what we do is we take this confusion matrix and we just say, let's draw this matrix, but let's assign costs. Right? So we have these costs, cost false negative, cost false positives, and one is significantly larger than the other. And the other two, so making good predictions is always good, right? So zero costs. Okay, now here comes the interesting part. We have this cost skewness on the one hand side, and then we have the class imbalance on the other side, because we have significantly more insecure cases than secure cases. So now two are interlinking. And I show you how. But first, let's reflect a second of what actually a classifier can do. Because it's not only to predict a class, security versus insecurity. So here you see 2 points, two points, which are both on the same boundary side. So we can both assign them as positive, right, as secure cases. But can we also rank them, because this one is maybe further away, that one is more secure or more positive than the other? So what we can also output from a classifier is a score S. So the score S of x gives us some sort of notion for how positive this x is. And now you can think, okay, if I can get this score, is this kind of a probability, right? Does this mean the higher the score, the more probable this will be secure? Or does it not mean that? So you can think that we can get these different things. We can rank points, we can output scores, we can also get probability estimates. But to get probability estimation is not that easy. So we cannot use the score as a probability. And I explain this on this example of decision trees. So if we take here this decision tree, which has 3 leaf nodes, right? So we have 100 points, 40 positive, 60 negative. So that's your training set, right? And now these points, you have trained your decision tree with gradient boosting or card algorithm, classification and regression tree algorithm. These points, they fall into these 3 different leaf nodes, right? So you can see here are 5 positives, 25 negatives, and so on and so forth, and the other ones. So you could think of that that as here in this leaf node there are 1/6 points positive, and here you have 5/6 positive, that if you have an unseen point from a testing set going into this leaf node, that you assign this number here as a score, and that it is possibly higher probable to have this point as secure than if you have another point in this leaf node. So the scores are essentially these values here. Okay? And we can use these scores to rank points. Now, we cannot use those scores directly for probability estimation. Because if you now assess this, if you plot this, probability versus the score, you see very often a distortion like this one. And what does this curve tell us? So if you now take a lot of points, you put this to your classifier, and you take all the points which have the score 0.1, right? If it would be a probability, 10% of these points would be inaccurate, and 90% would be accurate, right? But what you see in practice is that you get actually 100% accurate, right? And the same you can make with this example here. So if you take a score of 0.9, you get almost all of them accurate. So what you learn is this distortion, because the loss function is just penalizing misclassifications, but not at all how different these points are in terms of their probability, for example. But there are a few tricks, and this is what is called Platt scaling. So if you just fit a sigmoid function on top of this, you get something which is closer to a probability. So you can see you have just 2 parameters, A and B. It's just a simple sigmoid function. And this blue function here is S of x, right? And you now have fitted A of B on a validation set, for example, on your training set. And you get now this corrected output, this probability. And now this one can be used with a probability where indeed you have also inaccuracies. So if you would have the perfect probability, it would be on the diagonal, right? Because then the score would relate directly to a probability. Now, who has used language models recently? Okay. Not everyone. No one is using, okay, there were maybe 20%. That's interesting. I thought ChatGPT is now in everyone's computer, or at least the browser tab bookmarked. Okay, so who has used the temperature to tune a chat? 1, 2, 3. Okay, some people. Okay, what is the temperature doing? So the temperature is doing something very similar to what I have presented to you. So for instance, I go back to this example here. Tell me your electricity consumption, right, versus mayonnaise. And you see these probabilities. So if you have a model, a large language model, giving you different probabilities for these words, right? It could look like at 90%, the model says the next word is consumption. And maybe 0.1% it's mayonnaise. Right? So that's what is corresponding to a low temperature. Because the model gives you always then a very similar response. So if you tune the temperature, your ChatGPT, if you ask it the same question twice, you get the same response. If you put the temperature at 0, for example. So it determines some sort of the deterministic versus probabilistic functioning of the large language model. If you have a high temperature, these probability are tuned. So you may now get different responses. Right? So if you have a high temperature, the same question, you get different responses. With ChatGPT, sometimes you get 2 different responses. Right? So they may have just altered the temperature by a little bit, or just repeated it twice, because the temperature was not set at 0. Temperature can vary between 0 and 1, I believe. Anyways, I just try to make this connection, because what we do here is something very similar. So we can now tune these scores and the probabilities to make better predictions. And I'm going to explain this now. And that's also what cost-based learning or cost-sensitive learning is about, right? So you have now, you know this challenge, as I explained, you have these 2 different costs, right? So let's look again into one of those plots where you can select on this operating characteristic of a classifier where you want to operate it by tuning the threshold. So you have this threshold on the score. If the score is greater than 0.5, you assign binary 1. If it's lower than 0.5 or equal, you assign binary 0, right? But that might not be perfect. And the cost-sensitive learning is to tune that threshold. Right? I'll tune that temperature. That's the analogy. So for instance, if you want to have very high TPR, so true positive rate, you may increase the threshold so that you operate the classifier rather here instead of here, right? And you can actually compute the cost-optimal operation of this classifier by using this formula. And these 2 values, so pi 1 and pi plus, is the share of the positives and the negatives in your training set. Right? So it basically could be correlate to the probability of a contingency that it happens, so the probability of a fault. Right? And you have this one, which is the impact of the contingency. So I mentioned earlier that the insecurity, the power blackout is very bad, significantly worse than taking this corrective control. So if you just think about it and you assign these 2 as 1, so you have CFP and CFN equal to 1, and you have no class imbalance, so this means that pi minus and pi plus are both equal to 0.5, you get Z as 0.5, right? So that's the default. But if you now deviate and you have higher costs in CFP over CFN, you can tune now this decision threshold and change the decision threshold on the classifier for that problem. Right? Even though you have trained maybe on a balanced data set. So you take a balanced data set, no class imbalance, but you know there is differences in the class imbalance. You know there are differences in the costs, and then you use that classifier, you just tune the decision threshold, and you can optimize that for the use case you have. So it goes so far that that this probability of contingencies, you may have weather forecasts, and you see that there's a windstorm approaching, which means that the probability of contingency is now higher, right? So in real time, you can change that machine learning model to predict now differently there's insecurity or security, because you can alter the probabilities. And let's assume we apply that rule to tune our decision, the machine learning model. There are still risks involved, because we know let me go back to that plot. We know that this perfect classifier does not exist. Machine learning models make errors. Right? So you just need to decide what is more important. Is it the recall or the precision? Right? Let me go back now. And whatever you choose, you have a residual risk of relying on this machine learning model. And the first step to consider this risk, or compute this risk, right, is to decide or compute this secure, or the risk of security and risk of insecurity. So before making this decision, you may just compute this risk. So you have the probability, we have tuned our classifier, you get P hat, right? You have the probability of an operating condition, you have the probability of the contingency, and you have the cost. So this is essentially the risk of predicting secure. This is the risk of predicting insecure. And now you are predicting by choosing the lower risk, right? That's essentially what we do. It's another analogy to this cost tuning of the threshold. And from there, you can also compute then the residual risk, because you choose maybe for one point, the R secure is lower than R insecure, so you predict the point secure, right? But then that becomes the residual risk. So the summation of these residual risks is basically your total residual risk. So in essence, it works like using this decision threshold, the predicted one, in a more conservative way. So if you think about a classifier, right, and you have these leaf nodes, it really means to change the labeling on the leaf nodes. Okay, and that means to shift the boundary in your space. Now, what we can also do is to minimize this risk with hybrid approaches, because we can do some simulations, not so much. Maybe in the hour before, you can do a few simulations. So you need to be selective, what conditions, what faults you may want to simulate. So you first train the machine learning, use a machine learning model to assess all operating conditions. And you use now this risk, what I showed you, to run the simulator on those high risk points. So you rank all conditions, all faults, and you just take the highest risky operating conditions and fault combinations, and on those you are running the simulator. So you combine both worlds. This one is fast, sometimes inaccurate. This one is always accurate but slow, considering that the model and the power system is accurate. Yeah, and that's this combination of these two approaches. So what we were running is a case study on the French transmission system, where you can see that if you limit your computational budget, so you say I can run maybe 100 of simulations or 1,000 simulations in a data center, you drop the risk very fast if you apply this approach, than in comparison to a standard approach, which would just take random points to simulate, because it's not advanced. Okay, so that's the first half of this talk. We are also really at the break time, so then after the break I will continue, and maybe you have some final questions about this previous session?
Maybe one question before the break, and then, yeah, Nick.
Yep.
One question. You showed this slide about LLMs, and what I like about this LLMs, they provide a lot of foundational models, so-called. So they're trained on very different tasks, and then people can fine-tune them for some specific tasks. Do you see this as a possibility in energy domain, that maybe we will have such foundational models, and then people can fine-tune them for some specific tasks?
Yeah. So there is currently a research initiative which is called Grid Foundation Models. It's part of the Linux Foundation Energy, for example. So there's a project which looks into that. And the research community, there was a workshop in Argonne in February. So I attended that workshop also. And in September, there will be another workshop in RWTH Aachen University, which looks into that idea. So it's a growing research community, but the idea is to work towards grid foundational models. So the use cases so far, or the research there, is on AC-OPF power flow problems, but we also see then the very different tasks in the future. For instance, these time domain simulations or planning tasks or other things.
How it's called again, sorry?
Grid foundational models.
Grid foundational model.
Yeah, or short GFM. Yeah, so now I go to the second part, this learning models for secure system operation. So I hope this first part provided you with the understanding of this reliability management, what's important there. I mentioned this dynamic security assessment of one of the applications we have been working on, and then security assessment. So now I go through state estimation, learning with domain knowledge. So these are very connected topics, and then weekly supervised learning for secure operation, and closing with the challenges which are ahead of us. So let's go to learning with domain knowledge. So why do we actually need this domain knowledge? So, and this starts again with this story I mentioned earlier, that we have this issue of the curse of dimensionality. So the higher the dimensions, the more challenging it is to learn a machine learning model. But what if we can reduce these dimensions, right? And what if we can learn a smaller dimensional space? And that's a little bit where the domain knowledge comes in. So to induce bias, to induce information from the domain, from the electrical power system domain into the learning, like physics-informed learning or weakly supervised learning or other type of paradigms, to make machine learning practical for electrical power system. So let's maybe start this by realizing in what domains machine learning or AI is already very powerful, right? And we talked natural language processing, it's already very powerful. But another example is images. And then also we have these multimodalities nowadays, where you can ask with language something and you may get back an image and the other way around, right? So, but let's first, I know probably some of you know how convolutions neural networks work, but I start to mention them, the principles behind convolutions, so I can loop everyone in these graph neural network approaches. So with images, a few things we can note, a few properties we can note. So one is that if we look at an image, it very often comes down by learning from certain patterns in this image. So if you want to classify birds, for example, you can just snap out small parts of this image, and you can already, by just looking at this one, possibly infer that there is a bird in this image, right? By just looking at this beak. So what we would like to have is a beak detector, like something which can detect if is there a beak in this image, and then you could just have one function which says if there's a beak, assign the class label as a bird, right? But that would be very expensive to do this for all possible objects, right, and all possible images. So the first property we can imagine is that some of the patterns which are important for our pattern recognition task is that some images are already enough, right? So some patterns are much smaller than the whole image. And the neuron does not need to see the whole image, but maybe only just a part. But yeah, if we now have built beak detectors with different neurons, it may not be so efficient to do so, right? If you have a beak detector for this part of the image and for this part of the image, they are doing almost the same thing, right? So you can also just cut out this image and pass it through, but then the question, where do you cut out, right? So without seeing this, because a human, of course, can see it, but you want to have an algorithm to do that. Yeah, so these two neurons, if we would train it, would do almost the same thing. So we can use the same set of parameters for these different images. So the second property is that the same pattern appear in different regions, right? And you can think this as a translated invariance. So you move this around in the two-dimensional space here. Okay, the third property is that subsampling the pixels would not change the object. So that's called the subsampling invariance. So this means if you combine pixels here in a certain way, you get a smaller image. So the number of pixels is smaller now, but you can still use that to detect patterns, right? Because you can see it with your eye. The bird is still here. So the beak is also still here. So you didn't compromise really on the pattern. Of course, accuracy or the resolution is compromised now, but the pattern is still there. So this means if we do that, we have less parameters for the network because you have smaller patterns. Okay, so how can convolutional neural network learn using these three properties? So in essence, we have two different alternating layers, right? So one is the convolution layer, the other one is the max pooling layer, and they are using these properties. Okay, so the convolution neural network is, for example, here starting, you have the image on the left-hand side, and then you go to smaller dimensions. Right? So here's 224 times 224 times 64. So this is the image dimensions, right? And this is the dimensions of the neurons. And then you go forward. And then at the end of you have just 1,000 different classes, where the bird is maybe one of them. And then you have many other objects. That's how a convolutional neural network from the architecture view looks like. Now I can show you here how we can use these properties. So the convolutions make use of these two first properties. Right? So some patterns are much smaller than the whole image, and the same pattern appear in different regions. So that's what convolutions can do, or can use to learn effectively. And then the property number 3, the subsampling, the pixels will not change the object, that's max pooling, right? And then we are just alternating these steps, as I showed you in the previous slide, right? And that's how convolutional neural networks is essentially working. So let's now look into convolutional layers, right? So now we zoom into convolutions. So that's one of the two layers, so the blue part. So how do convolutions work? So I'm now simplifying here, and I just use binary. So you can think about black and white images, right? So binary here means not security anymore, but here we talk about black and white in the image. So 1 could be white, 0 could be black. And you see here a very small image, 6 times 6, and it has all these pixels on this matrix. And what you can now extract is this matrix. So you stride with green here. You stride over this, multiplying this with this matrix. Sorry, you are not extracting this matrix. You are getting this matrix. So you multiply this first 3 times 3 with this matrix, with filter 1, as we call it, to get a new matrix. You get this new matrix by moving through that image. This is your input image. This is your output image, right? And the matrix here is what we are learning. And, that's the parameters, your neural network parameters, in a sense. So let's have a look how this works. So let's assume you have initialized this filter, this matrix. On the diagonal, you have 1, 1, 1, and all other elements are -1. So now you move here over this matrix, and you see that you are multiplying basically just the diagonals, and you sum them up. So it's 1 times 1 plus 1 times 1 plus 1 times 1, right? So 3. And the other elements are 0, so you can just discard them. So you get this 3 here on the top left corner. Okay, now we do the same thing with the next 3 times 3 piece, so this piece, and you get the -1, and so on and so forth. Now you get the output matrix. Now you can have a different filter, so filter 2, and you can compute a different output. And what we are doing with convolutional neural networks is we essentially learn these filters, okay? So the filters gives you an entry here, and this 3 could now correspond with a beak of this bird, because they are detecting certain patterns. So the patterns we are detecting here is 1, 1, 1 on the diagonal, right? So if you have that here, and you may have that also elsewhere, you get both a 3 at the output. Okay. And you now focus on a small pattern in this image. So here's 3 times 3. You can just think about this, these filters. There could be many different variants, right? So 4 times 4, 5 times 5, and then you can focus on different sizes of patterns. Now with a lot of data, right? So a lot of labels, you can now learn these filters. Let's look into property number 2. So here I give you a different input image. Right? So now this is a different input image. This is the first one. This is the second one. So you don't have 1, 1, 1 on this diagonal, on the top left corner anymore, but you find this here. So the same matrix filter 1 detects that part now to be here. So that's the example I just made. Right? So if you have now the same pattern elsewhere in this image, you get here on the output also a 3. So the same pattern appears in different regions, and now we can detect this automatically. So right, we do not need to design big detectors everywhere in the image, but we have just one. But we are just going over the entire image. Okay, now what is max pooling? So max pooling uses this third property. So the subsampling of the pixels will not change the object. So these are the two images which we got. So the 6x6 image, we use filter 1 again twice. We get these different outputs. So that's the same matrix which I show you on the slide 60, and that's this other matrix which I showed you on slide 61. And max pooling, it pools these 4 values, for example, right? And it takes the maximum, max pooling. And you get now a 3. So you get another output, which is now 2 by 2. Now you can see that the detection of the object is still functioning because the 3 is maintained. It's now here still part of this 2 times 2 matrix. Okay, that's the whole point. That's how convolution neural networks work. So you first have these convolutions, then you have this max pooling. Now this is only illustrative. It's very simplified, right? So you have just a 6x6 image here. You have just binary, 0 and 1s. And you have, I just showed you one layer each, convolutions and pooling. But then in reality, they are alternating. But ultimately, you're backpropagating through all of those layers, updating your parameters, using a lot of data. Okay? And then you're learning these filters here. Okay, so that was a very quick intro into convolutional networks. Now let's go back to power systems. So, because in power systems, we do not have, I mean, yes, you also have images, but it's not the first thing which comes to mind when we talk about monitoring and control in this transmission system level control rooms, right? But what is interesting is that there is this generalization of convolutional neural networks to other geometric domains. And that's what is called geometric deep learning. So in geometric deep learning, you are generalizing this from, for example, grids. So grids is essentially an image to graphs, groups, and other geometries. Right? And that's also where very popular achievements have been made in the area of applying machine learning. So for example, molecular extractions, finding new protein structures without running a lot of experiments. That's basically using deep learning on graphs. Okay, yeah, and that's basically this story. So here, just the analogy between molecular graphs and n times n images. So now we have here 3 channels, RGB. It's not just one. So earlier I had just one channel with binary, but you have actually 3 red, green, blue, 3 channels, and here we have maybe m channels. So this could correspond to the type of atom you have here. Or the type of structure in this molecule. And yeah, then you can use the same kind of underlying techniques from convolutions also on graphs. Now, there are 3 different flavors of graph neural networks. So one is the convolutions, the other one is the attentional, and the third one is message passing. So with convolutions is the real analogy, but moving from image to graph architecture. So here I just show you one element, right? So one node, and you have multiple other nodes around, and you are learning essentially these functions which map the neighborhood n with that single node, right? So this ni is the set of these 4 different nodes, A, C, D, E, and you are here centering on B, right? And now you are doing the same, so you learn basically these functions, right? This is a neural network function, this is one function, and you move through the graph, Right? So you always, this is a one-hop neighborhood only. So you move from this node then to another node to learn these functions. Similar to what I showed you earlier with the image. Right? So you move from one part of the matrix to the next part, and here you do the same on a graph. So now you can, these have increasingly level of generalization or generality. So the next one is attentional. So here you can see they have different type of learning. So here you have attention function, which maps xi and xj. And here you have message passing. So it's more, this one would generalize to all the other two. Yeah, so the differences do not matter too much here, but if you're more interested, you can check out how they work and maybe apply also some of them as you wish. Okay, so this was the really primer about graph neural networks and learning with domain knowledge. So I have not really answered now, how does this now map to the power system? Okay, the only clue you may have right now is a power system can be assumed as a graph because you have these transmission lines, or in the distribution system, the lines, low voltage, medium voltage lines, and this determines the connectivity of your graph, possibly. On the buses, you have then generator or load injections, right, or also voltage levels. So yeah, that's the analogy. So to using the topology of the system as additional domain knowledge as to the physics-informed learning, that what I presented to you earlier. Okay, are there any questions about that part? Okay, I go on. Probably they come in this. Yes?
So the multimodal network, the way you drew that network is you don't have to deal with Kirchhoff's laws. It's basically just a set of linear lines. So how about if you used a 3-node network where the nodes were connected with each other, all 3 of them?
So if they are connected, I mean, firstly, these functions here are not linear, so they are nonlinear functions. Yeah. So we can learn also AC power flow between those nodes. But you have to learn these power flow laws in the first place. So it's not that we take the power flow and then we build upon, but the network needs to learn the physics.
I see. Thank you.
The only thing what we provide the graph network is the interconnectivity of the system. But what this approach strength is that you have the same physical laws everywhere in the system, in the power system. So if I learn something on one part of the power system, it also applies on the other part. So that's the analogy to the bird example. So if I have a bird here, it also is on the other part of the image. Okay. All right, then I go to the application of graph neural networks on the problem of distribution grid state estimation. So we move away now from these control rooms, from transmission system level, and now we are focusing on distribution grid level. But state estimation is important for reliability, right? Because of the question earlier, you have some measurements, you compute the state of the system, the steady state of the system, and from there you can do all types of analysis. So state estimation, distribution grid state estimation. So we start with a number of measurements, Z, M, and our measurement vector is Z, right, with noise from these measurements, so possibly Gaussian noise. And the goal is to estimate the full state of the system, so which is here 2n. I will show you in a second. That's basically the voltage and the phase angle. And then we have the state estimation problem, which is to get from Z to X. So this function f is now different to what I showed you earlier. Okay, so that's not anymore machine learning. It's just the general function you want to learn. And I have to say is that here I changed the notation a lot. So Z is the input, X is the output. Okay, in the previous part of the talk, X was the input, Y was the output. Okay, just for your information. So what is challenging about this distribution grid state estimation? So it is because of the observability of the system, which is generally low. So you do not have so many measurements in the system. That's different to transmission system level, where we can assume we have fully observable system. But in a distribution system, low voltage, medium voltage system, there may be differences on this, or there are differences on the observability, but generally we say this is partial observable, as we have just a few measurements only. So M is significantly smaller than N. Okay, so how could a distribution system look like? So you see here one example, which is the Oberrhein medium voltage system from Panda Power and others. They have this openly available. And you see the connectivity. So we have trafos, we have lines, medium voltage and high voltage buses. It's maybe difficult to see, but here's high voltage bus. There's a high voltage bus. And then we have power flow measurements. So we have here one, there's another one. So that means we can measure the power flow on certain lines. And then we have voltage measurements. And that's where you can see the scarcity. Right? So the red buses are where you have measurements, and all the yellow one, or orange, so these ones, you do not have any measurements. So basically, the problem of distribution grid state estimation is to estimate all voltages and phase angle on the orange buses from the measurements you have on this red and green illustrated points of measurements in the system. And what we also have available is the model of the power flow. So the full set of equations. So we assume we know the topology, we know our line parameters and other information. You can see them here, Y-bus matrix, and that's the full power flow model. And X is voltage phase angle, Z is this measurement function plus the noise. So this is the measurement function. Right? So it is essentially mapping the state X to the dimensions of the measurements to that. And here it's also illustrated, this problem. So you see these 4 buses simplified with buses and lines of what we plan to do. Okay, what is the classic approach to solving this problem? This is called the weighted least square approach, weighted least square method. So it's a numerical method. You start with an initial guess of the full state, so x0, and you have the noisy measurements. And this is, by the way, for steady state estimation. Right? So I don't do here any dynamic state estimation. So you start with these two, and now what we can compute is from the measurement function from x0. So k is the number of iterations, right? So we start at k equal to 0. So you take the initial guess, you plug this in your measurement function. So that's this whole function, and then you can get the difference between how well this initial state is explaining or mapping to your measurements. So if this is very different, then x0 was a very bad guess. Right? It's very large. So now we can express that as a minimization problem. So we have here the loss function. That's where the name comes out, weighted least square. So this is the least square problem. And this is the weighting by the noise level of the measurements. So maybe the measurements have different noise levels. So you're basically rating them. Right? So you basically rely on least noisy measurements more than on other measurements where you have high noise. Makes sense. Now what we can take is we can apply numerical techniques, Taylor series, and to compute this gain matrix. So these matrices are basically coming from this minimization problem. Right? So it's a bit out of the scope to derive you this, but it's a standard technique, weighted least square method. So you get from this minimization problem, you get this updating function. So the updating function here tells you how you update your state given this error on the measurements. Okay. and you update the state. You update the state here with this term, and you iterate basically until you have derived to a small error on the state. And then you stop. That's your final guess, X. Now, there are some issues with this technique, and there are a lot of literature which improve upon this technique. Right? So especially if you have partial observable systems, so this means if the measurements are very small, if you have just a few measurements, then you may sometimes not converge. So you have convergence issues. You have also possibly issues with X because it's a local method. So the question is how accurate is then the final state, even if you have converged. So yeah, there are some issues, and for transmission system state estimation, that's not a problem at all, because we don't have this problem. But in distribution grid state estimation, that is still a challenge. And yeah. Okay, now, so this is the conventional method I'm comparing our approach against. Right? And now there's a second conventional method I'm comparing our approach against, and that's the idea of using statistical learning. So that corresponds to what I presented earlier, supervised learning, so for surrogate models, right? So you collect a bunch of measurements and combination 2, y1, so this is the full state. So you use a simulator, you use weighted least square method essentially to sample these conditions, right? So you take the training set, you generate a training set, and you define this as an inference problem to learn from Z, so from the measurements to Y. So Y is now the state. So earlier I called it X, because X corresponds to the correct state, and now here it's Y. We define the loss function, whatever loss function you may choose. So it could be the squared error, and then you're learning for this. You can use any artificial neural network, for example, for this function. But the challenge is you need to create a lot of training samples again. And why would you do it? Right? I mean, because to obtain the label, you first need a method which works. So you need to do a lot of fixing, pseudo measurements to get also labels in the first place. So that's how this workflow looks like. So you start with the input noisy measurements that you have any feed-forward neural network, or can also be another type of neural network, or any type of model, and then you get the state variable x, and you have obtained labels y, and we basically minimize y minus x, right? So that's the loss function we apply, and then we tune our neural networks with backpropagation and so on. Okay, that's also conventional methods. So why is this not working well? Because the labels are not known, and you have also Newton's method, so that's the weighted least square method, which may generate errors in these labels. Okay. So what we have been working on is applying this concept of weakly supervised learning. So in weakly supervised learning, we consider that only the input of a neural network is inaccurate, but also the output. Right? So for example, y is now also inaccurate, and we plan basically with this inaccuracy on the labels. And now weakly supervised learning, yeah, in some cases you never get any. You always learn without any labels, right? That's one application of weakly supervised learning. Or you generate some inaccurate labels, and you can still learn something with these inaccurate labels. So that's the idea of weakly supervised learning. Then you design a loss function, and you basically learn this function such that you get something close to what you want to approximate the state here, or to learn for the state. Okay, so how does this workflow look like? So some of the blocks are familiar possibly now from the previous slides. So yes, we also use a neural network. We take Z as the input to the neural network to output the state variable X. What is now different is that we use also the measurement function H. Right? So we take X into the measurement function, So we do not require labels. So we do not have this loss function here, x minus y, which requires labels. So here we take the state estimation, so the measurement function h, and then we define this loss function just as we had it beforehand. So this is the weighted least square method, the weighted least square loss. So z minus h of xi, and we do the weighting again. So here I don't show RII, it's sigma I, but it's the same thing of the previous approach. So it's the combination of the weighted least square method with a kind of supervised learning approach, if you wish, but it doesn't require any labels. So that's this advantage. Okay. So that's now how we start to consider learning with the domain. Okay. So we use the power flow equations, such as physics-informed learning, right? We use the power flow equations, but what is currently and the noise measurement, but what I have not presented to you is that we also use the topology. Right? So then we have three pieces where we can learn from the domain of the electrical system to learn a neural network which can predict for state estimation here, or which can estimate the state. So let's look into this last part, topology. How can we encode the topology? And you probably can guess now the answer is graph neural networks, right? And that's now how these pieces from the previous part come together here. So what do we need to define to learn with graph neural networks? So first, we need to define what we mean by a neighborhood. And neighborhood here means the physical neighborhood of one bus to the surrounding buses. Right? So we have the graph, and the graph comes from the connectivity of the system. So we have vertices and edges, we have the adjacency matrix, Aij, which tells us if there is an edge, if there is a connection, then you assign 1, and if there's none, then it's 0. And then we can say, okay, we have a one-hop neighborhood, which is essentially for each node I, it has a different set of neighborhood nodes. Right? But it's exactly just one hop, so it's the direct neighborhood. So if we have 2 hops, then we would have larger sets, because then it's not only the direct neighbor, but maybe another neighbor. And now what we can assign is a neighborhood feature vector. So that's xni, right? So each node I has a different feature vector, which is just all of the feature values of the surrounding buses. Right? That's the xni. And now we learn these local functions. So the local functions take as input the neighborhood and the feature of that specific node. So think about that you have some measurements in the neighborhood, but not all of them. And you have also x0, right? So that's like your current initial state. So you take that and learn from the neighborhood that specific node. So the voltages and the phase angles at this moment in time that you think are present. That's what goes in. And then you learn these functions to estimate the state. Yeah, and that's a bit where these dots now connect. So we use convolution layers and message passing to learn these functions. So I'm not going into much detail, but it's essentially we learn these functions to exchange information between the neighborhoods, right? So how much voltage do I take from that bus and that bus, right? Which, yeah, you can see we learning kind of the physics, but also based on where we have measurements, right? So that's a bit the difference here. But we learn these functions. And here, just to map, I made this point earlier. The reason why graph neural networks are promising here is because you have the same power flow, the same equations across the network. So one neighborhood may look very similar to another neighborhood. And you can now use those information to learn smaller neural network models. So here you can see that we have maybe a lot of neighborhoods. You have some connections between those neighborhoods and the state estimation. So these blocks here are the labels you aim at. So these are the state variables, right? And you have these information values. This is the measurements, and the goal is to. Oops, sorry. So these are this is an illustration, right? So you have these measurement values, and the goal is to get there. So we do exactly still the same thing as I showed you in this initial problem statement of distribution good state estimation. Now, what I also need to explain a bit is what is called this deep statistical solver, because the solving process mimics a solver, right? So similar to a numerical method, we start at one iteration, and then we update our edges and vertices one by one, and we go over the entire graph neural networks. Right? So we initialize x as x0, so this is an initial state of your state estimation problem, and now we are updating our edges. So this is, just imagine this is a simple value right now, right, which we compute by neural networks. So you just use this equation where you have here two neural networks which have been trained, and then you're updating this MBA. Okay, so this is one value. And after you have done that for all edges in your graph neural network, you're moving to the next to update vertices. And now you have a different type of neural network which takes the M's, right, to update these guys. And these are now your local information you're passing through the graph neural networks, because it always takes the neighborhood information for that specific bus B. And then lastly, you update the label. So that's X, our state. So you can see that we have 3 steps here. And now what we do is we perform this from t equals to 1 to t. So similar to how recurrent neural networks would learn. And then we back propagate. Right? So that's the same strategy. So that's what is called the deep statistical solver. It was originally applied for power flow. And we have adapted this in our work to this state estimation problem. Okay, now let's look into the case study which we have been running. So this was done by the PhD researcher Benjamin Habib doing his master thesis, and then he was a PhD for a short while in my group. So there are 3 test networks we have been using. So one is the 14 bus system. We have been using the 70 bus system and the 179 bus system. And you can see the difference is in the connectivity. So you have here actually no connections. And here we have a few connections. That's the Oberrhein network, which I showed you already earlier. So 3 systems we assessed, and then he generated some data, varied around the Wisconsin noise around the loading condition. We assumed only balanced system, AC power flow. Then we varied noise levels for voltages and active and reactive power measurements. These are all aligned with, let's say, industry standards, these noise levels. Then a few of those to compare with weighted least square method, we assume pseudo measurements. So these are, of course, measurements which are have a significantly higher noise level. Actually, you cannot really have Gaussian noise there, because there can be the prediction of the loading of some households, for example, or of an industry. Right? So you have different probability, or you have different uncertainty on those pseudo measurements. And we used 3 different baselines: the weighted least square feed-forward neural network and the supervised DSS squared. So DSS squared is the deep statistical solver idea applied to distribution with state estimation. That's why it's DSS squared. But supervised means that we assume we have some labels. So we are just comparing how our approach, the weakly supervised approach, would compare if we collect labels. So we have a baseline for supervised learning, which uses the same model architecture that we have been using. And then a few hyperparameters we tuned, and we assumed also stable system, meaning that we are penalizing voltages which are, or we are regularizing with 2 strong deviations from voltages, around 0.95 and 1.05 above the scaled voltages. And the same we perform with loading and with phase angles. So these are the phase angle differences. Okay, and now some results. So first on the 14 bus system, so this is of the 3 systems, the smallest one. You see that the RMSA reduces when we train. So these are the training epochs. So in each epoch, we go once over the full data set, right? And you see that we have a reduction in the RMSE on voltage levels and also a reduction of loading levels. So these are the two parts of the state we were aiming to estimate. And now we take the 14 buses and we look into each bus individually and also comparing to the baselines on this slide. So you see the RMSE for WLS for the proposed approach in yellow, in orange, and the brown approach as DSS squared supervised, as I explained. And you see that they are all in a similar level, but the WLS is very high. So it was a challenging problem for WLS, but all of them are within reasonable ranges. So green would be acceptable, red would be too high. Right? So these are just indicators for us to evaluate what these values actually mean. So yeah, we see a good performance, but the DSS squared supervised is a bit better. So no major differences. Then the line loadings, you see here quite high errors. This was because we played around with model inaccuracy. So the transformers and lines were assumed as equal, and then we got these errors. So we have the same limitation as physical systems. If you have an inaccurate model, then you may also get very high errors. Just as if you have a distribution grid state estimator, a classic one, conventional one, WLS method, you also get inaccuracies if you as you assume the physics to be accurate. Now let's look into all of the results. So this is the 14-bus system just here in this table summarized. So we see voltage, line loading, trafo loading. Here I show you these two different ones. WLS is the green number. WLS has the best values for line loading trafos. Voltages are better for the supervised DSS squared, but yeah, also no major difference. Now it gets interesting when we go to the larger systems. So in the larger systems, you see significantly lower values for the proposed approach. And in fact, the WLS cannot provide outputs always. So this is this convergence issue in all cases. So we need to tune and play around with the convergence rate. So with some parameters which define your Newton's method to make them all converge, right? And you can still see in the 70-bus system that we have better performance. And in the larger system here, in this 179, we also needed to increase higher tolerance and more iterations. So simply speaking, to do even more tuning of the numerical method to make them converge. But in fact, we did in the 179-bus system, we only managed to make it converge to 53%. And that also now shows you this benefit. So it shows you two things. So firstly, we realize that in a larger system, we have higher benefits of the proposed method than in smaller system. Why is that? It is because we have now repetitive patterns. Right? Like just in this image, when you have birds in multiple locations, right? In one image. So one image, one state, or in the larger system, captures more information than in the smaller system. Okay? So, and the second thing we notice is that we have improved over this convergence issue. So the WLS method, we only made it conversion 53% of the cases, but and our method, it's not really, I mean, you always get a result. How feasible this is in terms of physics, that's questionable, but at least you get a result, right? And you can also evaluate the power flow equations afterwards and check how physically feasible it is. So there's no limitation on that, and you get at least a result. So computing time, also interesting to analyze. So you can see that that if we use WLS method, you have a 10 times increase to go roughly by 2.5 increase of system size from 17 to 179. With the proposed measures, you double roughly. And yeah, so next we studied different noise levels, so to explore the limitation of our methods. So we varied noise levels. So this is a default noise level. Then we say higher and lower. So this was this range of noise levels I gave you earlier in the overview slide of the case study settings. So this is low and this is high. And you see that the WLS method is influenced by different noise levels. That's also known. And what we see with our approach is that we get some noise cancellation through these graph neural networks. Yeah, for voltage level, it doesn't look very different. Oh, sorry, this was both voltage levels. Yeah, and what we then studied is missing data or erroneous data. So, for instance, we just assumed one measurement is not known anymore, right? A missing value. You just substitute that value with previous values, for example, just a static value, and then we are assessing how the impact is on WLS and DSS squared. Now, we see a low impact on the DSS squared, so our proposed approach. And the reason is that it is local measurements, local functions, local evaluations, right? So the missing value has just a local effect. That's how we can explain that. Okay. So interestingly is that the DSS squared was not trained to handle such events, right? And that's also what motivates us to go for this study. So we increased, we changed, we extrapolated, as in a sense, the loading conditions to values which the neural network has never been exposed to in your training network. So we increased, for example, generation and loading by 60% or minus 70%. And of course, we see an impact, right? So it's a statistical learning. I mean, you learn for your training set and the testing set you assume comes from the same underlying probability distribution as the training set. So if we now change the testing set and it comes from a different underlying probability distribution, you would expect to see significantly errors. Right? So it's nothing unexpected. Still, for some variations, so this is minus 30% and plus 30%, you see some nice results with the proposed method. So for line loadings, for example, you can still see, I mean, this was never been trained on these loading levels. Right? So it's minus 30% or plus 30%. And you can still see some reasonable results. So yes, there are limitations, but we can expect not to, let's say, a too bad extrapolation performance. But yeah, any general claim here would be wrong. Okay, so this was this part about graph neural networks and state estimation. Taking questions now. Quite a few, so 1, 2, 3, I guess. Yeah.
In the test cases that you presented, some of them were meshed, where others were radial. Was there any difference in terms of the capability of the models to learn if it was mesh or radial networks?
Yeah. Yes, definitely. Was major influence. So it is one of the size of the network, but also as we are learning through the neighborhoods, the information can propagate faster if we have meshed versus radial. So that's also determines the success of the method, which is also why we explore it currently more for medium voltage system and not for low voltage system. But yeah, also in low voltage system, we have, at least in the Netherlands, a few connections now of the ends of the network, so it becomes also a bit more meshed. So there could be possibilities there as well.
Your loss function now includes these power flow equations. Does that not bring any issues in going back propagation through that highly nonlinear thing?
Yeah,
and how do you solve that?
Yeah, that's, I think, a difficult question. So the full loss function is here, right? So that's this on the right, here.
Yeah.
So we have now this physical system here. We have additional loss terms, so tuning those parameters. Here, for example, lambda, I didn't show them for the other equations, but it's generally challenging to tune it. So I don't have a good answer how to solve it for all possible problems, but yeah, it's difficult. I mean, it's a lot of instabilities which can happen during the training. Tuning those parameters is quite important. Okay. That's for sure. But yeah, we here used just one instance of these parameters and did not use an exhaustive study of the parameters. So it was more testing a few parameters, or a few of those lambdas to balance the loss terms. What for sure helped was to include these terms. To assume a stable system. Because otherwise you get, in the initial phase of the voltages which are extremely high and which are unrealistic and unfeasible. So at least the neural network quickly learns what are expectable ranges.
I see, thank you.
Yeah, thank you for the presentation. I was wondering, looking at the test cases that you showed for the larger grid, you allowed more tolerance for the WLS, so it can converge at the cost of having larger errors, but it still had lower errors when it comes to line loading compared to the medium grid. Do you have an explanation for that? Why it was better?
I could imagine that it relates to that they have different level of partial observability. But yeah, we haven't looked into why this difference is. But I can imagine it's related to that maybe in one system we had more measurements in comparison to buses than in the other one.
Okay, maybe if I may ask a second question.
Yes.
So you chose where the nodes that you have measurements at. Did you experiment also having the same number of measurements but at different nodes, if that also generalized well?
We didn't.
Oh, okay. Yeah, thank you.
Yes, thanks.
Thanks for the presentation. You said that you were looking at steady state estimation. So I was wondering how dynamic state estimation would look like and if it's a use case for neural networks.
Yeah. I think there are a lot of, I mean, it can be explored. I haven't looked into it. Baselines then would be Kalman filters, extended Kalman filters and other techniques. In my group we have not worked on this for dynamic state estimation, but I can also imagine there are investigations which are reasonable to go there. But then this would be to figure out what's the limitation of extended Kalman filters and similar techniques which can do that. So in our case, we only focused on the limitation of WLS method and then focused on how can we resolve these challenges.
I just had one question on the slide where you introduced the epochs. I understood them as learning cycles, but you see basically that the RMSE goes down and then it jumps up again and then it goes down. I was wondering what the reason behind this is, or if you have something.
Yeah, I think that's, I mean, during this training, there are a lot of adjustments in the learning rate, for example. So the learning rate is adjusted throughout. So you may have a high learning rate at the beginning. Right? You update neural network parameters maybe too much, and then the learning rate is adjusted to be more sensible, if you want. And then you learn at a different learning rate.
Because you see the same on the left, basically, as well, right?
You mean here?
Yeah, no,
yes,
a bit more to the, even in the beginning of the cycles, basically.
Yes, okay.
Yeah.
Yeah, I think that's, I mean, it's not an untypical pattern, I would say. Yeah.
Any other question?
I have one specific question on the loss term in the GNN case. I noticed that all of the, I guess, terms share one regularization lambda. So do you have a sense of why is that, or just what's the thinking behind that? And also broadly, can you tell us more about the trade-offs between different approaches at just incorporating physics violation constraints into this type of problems?
I can thought. Like this one, we cannot propose this as the best way to do regularization. So it's just one way we do it. So it wasn't part of our research But it's for sure, like similar to the question earlier, is for sure very important to answer. But we haven't done that. Thanks.
Good. We can move on.
Yep.
No, one question.
Yep.
It looks like in the previous one, where you had the penalties for voltage, could that be forcing an unstable system into a stable system?
Yeah, it could be.
Okay.
It's a limitation. So we assume a stable system.
Yeah.
But yeah, you're
but
right.
if you're looking for the unstable systems,
Yes.
this may.
Absolutely. I mean, I agree. It's a limitation of the method, or at least of these loss terms here, that we would not be able to detect an unstable system. Yeah. Okay, thanks for the questions. Then I move on. Okay, the end is 5 p.m., correct? Okay, perfect, thanks. Okay, yeah, then I will present this work, which is done by one of my former master students, who is also here sitting in the back. Hi, Bastian. And he's now a PhD researcher here at DTU. So, yeah, where does this research start? So this is another example of weakly supervised learning, right? So weakly supervised learning for secure operation is the subject. And now we are looking still in this area of reliability management, but now not on state estimation, monitoring, but we go to control and to making operating decisions. So what we investigated here is the security constraint optimal power flow problem for n minus k. So k is the number of faults simultaneously could occur in the system. And you are interested to find operating generation dispatches, right? So you had ACOPF probably in this morning. So here we look into security constraint optimal power flow problem, making DC assumptions. And we are interested to get this generation dispatch, PG, right? We have the demand, PD, and the goal is to get PG as cheap as possible. But also the expectation is that we can secure against n minus k faults. So n minus 1, n minus 2, n minus 3, for example. So this PG needs to be secure against also those cases, or the combination of PD and PG. Okay, so the conventional approaches don't scale very well with the number of simultaneous faults, k, right? So for the SCOPF, it really means that you are combinatorical exploding if you go to k, higher than 1. So let's look into just very briefly what the SCOPF looks like, what assumptions we made. So you have the classic linear objective function of the generator costs. Then you have here the generator constraints, PG minus PD, and the phase angles and the B matrix. And then you have limits on the generators. So PG min and PG max defined for all generators this maximum and minimum. And then you have the same for line flows. So we assume these limits, right? That's our DC optimal power flow problem. Now, if we use the SC OPF, we expand with a list of additional inequality constraints, which is the line flow limits. So for each n-1 fault, or for each contingency scenario, you add one inequality. Sorry, not one, but one for each line. So you have L and C as the 2 dimensions, essentially. Now, this is where the combinatorial complexity comes from, because if you have now n minus k, you need to, or n minus 2, for example, you need to combine each n minus 1 fault with another n minus 1 fault. So combinatorically, it really explodes in the number of inequality constraints. So conventional approaches can solve also this large optimization problem, but they may be slow. It depends, of course, what approach we are taking. So there are Bender's decomposition, there are Kalman constraint generation approaches, and I'm sure there are many more others here which are significantly more advanced and knowledgeable about this topic. And then we have also the line outage distribution factors. the so-called LODFs. I will introduce this in a second. And then what has been also explored is machine learning approaches. So they often rely on label training data. This means that you are generating labels by solving the n-k security constraint optimal power flow problem. Right? So you rely on labels which require quite some computation. So you can sample all PDs, you can solve a lot of optimization problems, get these labels, which is essentially now the generator dispatch, PG. Right? So this is also intractable for increasing K. So the line outage distribution factors, what they can do is they take the F0, so that's the line flow pre-contingency, they multiply it, it's just a large matrix, and you get the line flows for the contingencies. So let's say one matrix can give you for one contingency these new line flows. Right? Now you can take FC and you can just check with an if clause if they verify the inequality constraint, this one here, with, after solving the optimization problem. Right? So you solve just this optimization problem, the top part, DCOPF, and then you can use the line outage distribution factors on that solved instance, and then you can check afterwards if these line falls applying these LODFs are within this domain or not. And then you get some information. Or you can assess this post-fault security. Okay, that's one thing. The other box I need to open very briefly is what is called the probabilistic security for n-k faults. So you can think about that someone can compute probabilities of line faults. Right? So you could think about the Dutch coast, this is the Netherlands, and maybe you have a wind farm, a storm which hits the Dutch coast in this region here. So this means that if there are line faults at the same time, it's more likely that these two line faults happen simultaneously in this area than the blue line and this blue line. So you see here the correlation coefficient versus the distance between two branches. So the distance of these two blue lines is much higher than the two red lines. So the correlation between simultaneous line faults is higher. Okay, and now you could think about it that someone can update these probabilities in a day ahead or in real time, right, based on weather forecasting models. So that's probabilistic security. So we are interested in investigating the probability of being secure instead of being deterministic secure against n-2 faults using these probabilities of line outages. Oops. I hope the mic was on previous. Now I realized how loud it can be. Okay, so now what is the proposed approach, proposed by Bastian primarily? So we never use any labeled data. That's the key benefit here, right? So you this falls into this weakly supervised learning approach. So we essentially, I'm going to show you how we do it, but it's you are learning for an n-k security constraint optimal power flow problem without never solving the n-k security constraint optimal power flow problem, right? So we are not using any labels from any optimization problem, from the full problem. Okay, so there are a few contributions of this work, which was presented at PSCC in 2024. So we have the deterministic. So first we focus on deterministic case, then we go to probabilistic security case, and there's one approach which where we use a reduction of the computational graph to make it feasible to learn, because computational graph is basically in a neural network. You forward pass, right? You have the chain of functions, and then when you do backpropagation, you have the derivative of the loss function to update your neural network parameters, and that computational graph gets very large, right? So if we learn for, I will show you this in a second, if you learn for this problem, you get a very large computational graph. So the question is, how can we reduce it? But I will get into this in a second. let's first look into how have we built this approach. So the first step is that we use a neural network to take PD as input to give you us generation dispatch. This is your PG head, right? So then what we take this PG head and we solve one optimization problem, right? So this can be this is a linear optimization problem. You have PG minus PG head. So it basically, and then G and H are your line flow limits. So this is the same as what we have here, just this upper part, in a way, where we modify the objective function. So the objective function is not this one, but is, sorry, am I? Oh yeah, here. Is this difference to the PG head. Okay, so the neural network gives you PG head. We minimize to the closest physical feasible generation redispatch, given the pre-fault conditions. So that's the feasibility, what we call feasibility restoration. What we also get from there is the phase angles and the FL, so the flows of the network. So we take those and we use now the line outage distribution factors to compute the post-fault FCs. Right? So this evaluation is not part of the optimization problem. So that's the trick. So the idea is we can take now a loss term to update the neural networks. So to decompose this a bit. You have a neural network which predicts you PG. You have an optimization problem. Yes, it makes it a bit slow, but it's a small linear optimization problem. And then you can use that output of the optimization problem for the line outage distribution factors. These give you the FCs, and then you can perform backpropagation on mismatches and errors on post-fault too high line flows, let's say. And that's the way how we can learn an n-k secure generation dispatch. Okay, so here is the list of all the loss terms. So it's not getting easier. The loss functions get more. And yes, it is tricky to tune those. But again, I'm not focusing on this too much. But it's future work. I mean, it's for sure has to be answered. So we have now a number of loss terms. So this is, you know that dispatch cost, that becomes also part of the loss function. You see the full loss here. And then we have the line flow violation pre-contingencies. We have line flow violations post-contingencies. So that comes from the line outage distribution factors. And then we have power imbalances. So that's another term which we added. So these are all weighted in a different way. We have these numbers here. And you get a loss function which can learn now this neural network. That's the idea. Okay. Now, to make it probabilistic, what we can include is to weight this loss function slightly differently, because one probability may be, one contingency may be more likely than another one. That relates back to this one here, right? So n-2 with these two lines is less likely than this n-2. So why do we not use this information directly in the loss function to focus on probabilistic security, right? So that's this extension from deterministic security to probabilistic security. Yeah, so now you can imagine that also this matrix is a large matrix, the line outage distribution factors, and you get a large computational graph here, which means that if you want to do backpropagation for a lot of contingencies, it is not so practical on a standard computer. And what Bastian came up with is to use the sparsity to only store the gradients where which you can backpropagate. Right? So you exploit the sparsity, which in the different systems is quite high for n-1, n-2, and n-3. I show you this here. So you have only a few entries, if you wish, are leading to line overflows, right, of the set of C, of all your contingencies. So those are the ones you are essentially taking to backpropagate to your neural network. So it's only this red part. So if you see these entries here, a lot of zeros, they don't lead into line overflows. So you are getting rid of them, and you only take a few of them for backpropagation. Okay, let's go into some case study. So we used two systems, 39-bus system and 118-bus system. A few came from 1 to 3. We have also the code available. So these are the two systems. And now what I should mention is that we have ignored or not considered islanding cases. So we removed all islanding cases. So for instance, if you have here n-2 on this area, this would be an island, and we are not considering this as a contingency we are catering for. And you can see that there are significantly more islanding cases if we go to higher order of outages. It's also clear, I guess. If we look into the computational performance, now on the one hand side, you can use this large security constraint optimal power flow problem, which considers n-1, n-2, n-3 faults. You can do that, but you get quite high computations. Once you have trained the neural network, then the computation is very fast because it's just a forward evaluation and the small optimization problem, which you have to make it physically feasible, right? So the ultimate PG which you get is still physically feasible, right? Because we have this feasible restoration. And that's what determines this green bar here. Now you can see some cost reduction for n-3 particularly, but maybe good to say is that in reality often we cannot solve for this problem because it's quite slow. Yes. Okay, now let's look into these two issues. So you have an n-3 proposed approach. These are line overloads, number of violations in this area. And you see with the baseline, we have higher line overloads than in the proposed approach. Here I just zoom it in. And this shows the reduction of the computational graph. So just looking into the forward pass and the backward graph, I think. So this is the backward pass only. Let's look into the forward first. So we take the full graph, we have the reduced graph. So there's no much reduction or change. Apart from here, actually, we need to do some analysis. So that added already up and was then worse. But that's only the forward pass. The backward pass is where you have the big benefits. Because that's where you compute the gradients and you have this big reduction in n-5, for example. Okay, so I think I will stop it here and go to the conclusion. There are just 3-4 slides, but I think I will just leave it to 1 or 2 questions. But I will summarize the challenges. So we have generalization is one of the challenges which we still need to work on, data efficiency and model inaccuracy. 3 challenges, which I think I motivated anyways earlier, right? So at the beginning, when I showed these different machine learning concepts, you see repetitive challenges, model inaccuracy, generalization capability. These are the ongoing challenges we need to work on. Now, of course, for many decades, AI has been investigated for this power system reliability, right? So I showed you examples from the 90s. So this is, of course, promising concepts, but now we have new techniques, we have new data in control rooms, which I think is even more promising to look into this research more. And the 5 research challenges, I mentioned them. Curse of dimensionality, addressing these risks, and we still need a lot of data addressing this curse of dimensionality with smart concepts. So for that, I think I conclude, and thank you very much, and I take maybe one question. Yeah.
I know many of you should leave on time, so maybe only one question. Yes.
Thank you very much for the presentations. I have a question regarding, you mentioned the system cost very briefly, and if I got it right, on the right-hand side you have the machine learning approach, and how can it be cheaper if it's constrained by the same feasibility space?
Yeah, good question. So we have actually, for the baseline, we have not solved the n-3. Okay, so for all cases. So that's why we get higher costs. So we only consider n-1 because in the 118 bus system we cannot solve the full problem with all possible line contingencies.
Good. Please join me to say thank you to Jochen again.
Yeah.
Thank you.
Thank you.